All right. Next section here, we have left multiple integration, and we are now in chapter 16, which is all about vector fields and line integrals. So, 16.1 is a vector field. It's our introduction to vector fields. So first thing here I want to talk about is this operator, nabla. You can call it that if you'd like, but the important thing is do not call this, when it's by itself, the gradient. The gradient is when it's acting on a function, a scalar function. In other words, a function that spits out a scalar, not a vector. This by itself, it would be incorrect to call it the gradient. But this symbol here, and subsequently this vector that has instructions to take the x, y, and so on and so forth, partial derivatives, it is used to define the next two things. So the divergence operator. So in addition to the gradient operator, we have the divergence operator. So the divergence can be written as either function notation, like saying you can write absolute value as vertical bars, or you could write like ABS of -2 equals 2. So this is just that other notation. Most of the instructors are going to use this notation for the divergence and curl operators. So the divergence is taking this nabla and dotting it with a vector field. So if you do the dot product, remember the dot product, we're just doing the component-wise multiplication and then adding it together for each pair of components. So the divergence of a vector field looks something like this. What is the divergence? For the exam, you won't need to know conceptually what the divergence tells you, nor will you need to know that about the curl. That's better suited in like a physics setting to give you some more concrete examples. But roughly speaking, the divergence tells you the extent to which your vector field is outward at a point. So how much of the field seems to be flowing outward from that point versus inward. So a positive divergence means there tends to be more flow out, and a negative divergence tends to mean there's more flow in. And if it is a zero divergence, then at that point there's about an equal amount of flowing in, flowing out. But again, you will not need to use that interpretation. Moving on to the curl operator. Again, we have the different notation. You can say curl of a vector field f, or you can do nabla cross f. So it's defined as a cross product between nabla and your vector field. So make sure you are up to date and brushed up upon cross products and evaluating them. So I have it all written out here in this big, bulky, clunky mess, just so that you can all see it and have it. But really remember here that in general, what we're doing here is when you take a cross product, you are doing something like you really have your del f3 del y minus del f2 del z I hat minus del f3 del x minus del f1 del z j hat. This is the thing. Don't forget about the alternating minus sign in the middle there. Plus you'll have your del f2 del x minus del f1 del y k hat. So that's exactly where these things are coming from. What is the curl? Again, like the divergence, you will not need to use or know this interpretation of the curl, but the curl tells you the extent to which a vector field is rotating. It's a measure on the rotational character of your field locally at a point. Things that are important to know here is the following. It's not written here. I mean, it is, but it's implicit. I want to make this very explicit. So for gradient, you take the gradient of a scalar function and it spits out a vector field. So the gradient of a scalar is a vector. Divergence. You take the divergence of a vector field, and the result is going to be a scalar. Notice down here, we had a vector field, took the divergence of it, and the result is no vectors, a scalar. So the divergence of a vector is a scalar, and the curl of a vector is a vector. It's a vector field. So that's important to know. So you cannot take the gradient. It would be incorrect to say the gradient of gradient of this is nonsense. You need to have a dot or a cross, right? This is nonsense. All right, last thing for this section, 16.1, is a vector field F is conservative if there exists a scalar potential function. So this is the first time that we defined conservative vector fields, right there. We have a whole section, 16.3, dedicated to conservative vector fields, but this is the first time the definition does appear. So the definition is simply a field F is conservative if it is the gradient of some function.